Okay, so again, thank you very much for the invitation to participate in this event. I don't have that much to add to what I said the other night about Spenta. I have a great admiration for him, for his work, and for his efforts, and to keep to help keeping this community very active. I'm a big admirer of India, in particular of Indian science, and coming from a developing country, I think having such a top group here is a role model for all the other developing countries to say that it is possible to achieve what you have achieved. So it's very inspiring for us to know that you have these groups here. And yes, I said the other day also that to be a director of ICTS, you have to be a winner of ICTP prize. So Spenta, Rajesh has, I think, inherited this challenge very well. So I wish you the best. And actually, well, this year's ICTP prize winner is here. so you never know. Okay. So, well, I'll be talking about something on nilpotent superfields, something that has been becoming a little bit active in the last few years. People working on mostly trying to work on inflation and supergravity theories they have found that nilpotent superfields can be useful for that. But I'm not concentrating on inflation at all. I'll just see how we can use these nilpotent superfields in the context of 2P string compactifications, in particular for modal stabilization on the Sitter space and supersymmetry breaking. And this work started with a collaboration with Renata Carlos and Angel Uranga. Actually, part of this was done here while doing the Strings conference in 2015, and then follow up in some other collaborations. So let me just remind you just to have things clear about these nilpotent superfields. So usually in supersymmetric theories, in the string compactifications, we have the particles fitting into chiral superfields, the matter and moduli fields fitting in chiral superfields, and with the standard components, the scalar, fermion, and auxiliary field. However, you can impose further constraints, and in particular, the simplest one is impose the nilpotency, x squared equal to 0. And that you can do as a way to essentially represent a non-linearly realized supersymmetry, in the sense supersymmetry breaking. And in particular, when you do that, you can follow the standard rules of supersymmetry with the Kahler potential and superpotential. And being nilpotent, the most general superpotential is linear, which is very good. And of course, the Kahler potential, you can go beyond quadratic. And so the scalar potential you can compute, and essentially positive. It's just a constant, the same constant here. And since that will just contribute a positive term to the scalar potential. And that's what people have been using that to get the Sitter. So, of course, there's not this. You can do it. Of course, this is always true in global supersymmetry, because but in local supersymmetry you will get the same structure, because x as the scalar component of x is no longer a field in your spectrum, and so in that sense you can use also this for supergravity, and this is a nice way to represent the standard Volkov-Akulov representation of nonlinear realized supersymmetry in terms of superfields. So this old story started with Rochek in the 70s, I think. Somehow it was revived by Komargowski and Cyber a few years ago, and then several people have been following up applications for that. So now just keep in mind this, and when we can use this to use it for string compactifications and model stabilization. Okay. So let me just remind you about the string scenarios for model stabilization. For different kind of string theories, there have been the most developed scenarios for model stabilizations are the KKLT and the large volume scenarios in type 2B, and I will concentrate on this essentially, that there's nothing wrong with the other ones except that nothing has not a proper discussion about model stabilization has been achieved in all of them. So, to remind you, this for model stabilization, first you start with the GKP, the Giddens-Kashur-Kulczynski, where you start with the fluxes in the 3 cycles in the Calabi-Yau, and you have the Gukov-Witten superpotential, G, H, omega, where G is a combination of the F3 and H3 that can have quantized fluxes, M and K, and that fixes the complex structure moduli, the sizes of the 3 cycles, Z, and the dilaton S. So that was the big achievement of GKP. And on top of that, you can get the complex structure moduli give you that some of the 3 cycles give you this warp throats, and the warp factor depends on the exponential of the ratios of these integers, and that's how you get this warp throats in the compactifications. Okay. Unfortunately, of course, you know the GKP scenario only fixes one part of the moduli, the complex structure, but not the Kahler moduli. And the Kahler moduli, at 3 level, they are just flat, so they're completely unfixed. However, we know that by quantum corrections, they will give you runaway behavior. So in that sense, this GKP is unstable because you have runaway fields in the Kahler moduli, so the size of 4 cycles and 2 cycles. Then that's a KKLT. I don't know if Sandeep is here. Maybe he's left. Huh? Yeah. He left. Okay. So that's okay. I'm usually critical about KKLT, so in that sense. but since he's so powerful now, no, I have to say I have some good things to say about KKLT. So what they add in the 4 cycles non-perturbative effects, going like e to the minus t, where t is the sizes of 4 cycles, and that fixes the Kahler modulus, and they consider only one single modulus, and that's fixed by non-perturbative effects combined with the flux superpotential of GKP. And but contrary to GKP, now supersymmetry actually is preserved, and dw equal to 0, and then that means that you have a supersymmetric ADS. And what they did is to get the sitter, they add an anti-D3 brane at the tip of the throat, and at the tip of the throat, they add a positive contribution to the vacuum energy, and that will give you an uplift. And the uplift is a coefficient here that depends on the warping, and then divided by the volume to some power. And this power was given to be 3 in KKLT and 2 in KKL-MMT. Now we see it in a way that it's 3 when you don't see warping, and it is 2 when there is warping. So essentially, this is the right structure. And the reason I used to be critical about the KKLT is that this anti-D3 brane is just put in by hand, and it's breaking supersymmetry explicitly. And so then in that sense, you lose control of your effective field theory. And of course, people say, well, since it is in the warp region, so you can control how it is, and still this will work. And I think at the end it's correct, but this is just to give you the warning. And then we came up with the large volume scenario several years ago already. And this is essentially the same structure, but you have to take into account the quantum corrections to the Kahler potential. And once you do that, you have the whole scalar potential. You have you can classify in powers of 1 over the volume. The leading order goes like 1 over volume squared, because you have to have that to get the string scale, because all this is in units of Planck scales. So, and this is the leading order. This is positive definite, so the minimum is when each of the 2's are 0. And that fixes the dilaton and the complex structure moduli, as GKP had done. But on top of that, you have this extra 3 terms, which give you the next two leading order correction. They will go like 1 over volume cube. And if you have more than one modulus, tau and the volume, then they can combine to give you the minimum at volume e to the a tau, and that's why it's exponentially large. And so this will give you the minimum. And for weak coupling, tau is proportional to the 1 over G string. So G string is small, so tau is large, and then the volume is exponentially large. And contrary to KKLT, this minimum actually breaks supersymmetry. And actually the supersymmetry, the source of supersymmetry breaking are the fluxes of GKP. And still, then the simplest case gives you ADS, but you can complicate it and have matter fields and so on, and there are several ways of getting the sitter. For instance, not only anti-branes, but you can have f of d terms, hidden matter, and so on, something we also can be understood in terms of what people call T-branes, and other effects, non-perturbative, and so on. You can have other sources of the sitter, so you don't have to rely on the anti-3 branes. And at the end, the scalar potential takes the shape like this, where you have the standard, so the large volume piece plus an uplift part. The uplift part is, I mean, it's just written here, but all this is the same scalar potential. It's not adding up. It's just to keep track of it. And at the end, you get solutions which should have positive vacuum energy. And the nice thing about this is that you have a small parameter, which is 1 over the volume, and that will give you the hierarchies of scale between the string scale, the Caruso-Klein, the Gravitino, and so on. One particular feature that I always emphasize is that the mass of the volume modulus is hierarchically smaller than anything you find, is that compared to the Gravitino mass, which is the standard, and which is power 1 over the square root of the volume. So this field is particularly dangerous or interesting, but it's also generic, so it's always there. And more generic is also the case that its axiom partner is essentially massless, and the mass can be e to the 1 of the volume, which is essentially 0. And that can be very interesting for issues about very light dark matter that are fashionable now, or dark radiation. And you can compute the K rate goes like e to the 1 of the volume cube. So the volume helps you to keep track of all the scales.
The effective coupling constant that you get between the volume moduli and other fields, is it all suppressed by 1 over V?
Right. All this, exactly. It's essentially Planck suppressed. Okay. So one that I have said all these things about against anti-D3 brane, I will just reconsider it, and that's why we are using the nilpotent fields. So that yes, you can start with KKLT, with the -3 log of t plus t star. This is the simplest Kahler potential, I mean, for one single modulus. And then you can add a nilpotent superfield X with some Kahler potential with t plus t star to some power n, and plus matter fields. And the superpotential will be the flux superpotential, the non-perturbative part, matter part, and the nilpotent part, which is only linear, rho times x. Plug this into the supergravity action. That will give you the VKKLT plus uplift. And the uplift takes this form. And for particular values of n, that will give you the KKLT or KKLMT that I mentioned before. So essentially, by just introducing this field x, it gives you the same effect as the anti-brane was doing for you. So in that sense, this is but of course, in this sense, supersymmetry is explicitly, I mean, you're working in a fully supersymmetric action, so you can control your calculations. So that I think that got me attracted to this, because I think now I can see, I can do calculations with a supersymmetric effective theory, because everything is being done in terms of the X superfield. So in some sense, the X is representing the presence of the anti-brane. So, so what we did with Kahler and Uranga is to say, well, let's try to implement this in an explicit way in string theory. So we took a conifold compactification, or orientifolded conifold, and in such a way that you have the throat here, and the tip of the throat is also the fixed point of the orientifolded. And in here, we've computed the spectrum of the anti-D3 brane, put an anti-D3 brane here, and compute the spectrum such that the twist of the orientation project out some of the states, and the fluxes of the throat give mass to some of the other states. And at the end, what you are left in the anti-brane, the only mass state is the Agostino. It's a fermion, it's a massless fermion, which is the Agostino. And then, because we know that the bulk of Akulov action for the Agostino is reproduced by the X superfield, so that shows that this is explicit representation of the nilpotent superfield in string theory. So essentially, that's what it is. So up to here, it looks like an analogy, and here it looks like this is a realization, that you have the spectrum of the anti-D3 brane is precisely the Agostino. So you can see, well, here the fluxes give mass to the other four fermions in the brane are given masses by the fluxes, and the scalars and gauge bosons, they are projected out by the twist, and at the end you have a realization of the nilpotent superfield in terms of the anti-D3 brane. And with Iñaki and Roberto, but we extended this to have and the representation with the Uranga and Kahler, it was only a local case, so then we did that in a full-fledged Calabi-Yau compactification, the real compact Calabi-Yau. And here's all of the historic data and so on, that also realized precisely this, the anti-D3 brane giving you a nilpotent Agostino in a stringy context. Actually, we realized that I think this is the first concrete realization of the warp throws the KKLT in a compact Calabi-Yau, which is curiously after more than 10 years of KKLT. Okay, so how can we use this for supersymmetry breaking? For uplifting, I think it's okay. You can just add the anti-brane. People were happy with that. That may be okay, and we'll just be reformulating what we had. But if you want to compute supersymmetry breaking in an observable sector, what people have done in the past using KKLT and so on, in particular for KKLT, it was very difficult to extract what supersymmetry breaking effects were because of the nature that the Lagrangian to start with was manifestly non-supersymmetric. So, whereas now we have a manifestly supersymmetric Lagrangian, so we can use the standard expressions for supersymmetry breaking in the observable sector. So you have the Gaussian masses, trilinear terms, and the scalar masses. And these expressions have been known for many, many years. And now, then the only thing we have to know is what the K, Z, and the superpotential and the gauge kinetic functions are. You plug them here and just get the expressions for the Gaussian masses, scalar masses, and so on. And so we'll consider, as usual, the standard models. The standard model is either on a D7 brane or on a D3 brane. And these are the two possible realizations. And then so the anti-brane is far away, some other place. And, in that expression, after KKLT came up, there was this paper of particularly Choi et al. In 2005, where they tried to extract soft supersymmetry breaking. They were not using the nilpotent superfields at that time, so they had, I have to say, complicated expressions for trying to extract the soft terms from the anti-D3 brane. And that is the state of the art. That was the state of the art until now, until what we came up. And they computed the masses of the moduli fields and the soft terms and so on, and they had particular expressions for them. So what we did is just to revisit this calculation and do it in using the nilpotent superfield, which is manifestly supersymmetric. So now we have the superfield X. The F term of that you can compute. The F term of the moduli fields you can compute, and then you can compute the Gaussian masses, scalar masses, and trilinear terms, and you have general expressions for them. So. For the for the case of these people, they did it only for D7 branes. We did it for both D3s and D7. So in that sense, that we have new results, and also we differ a little bit on the conclusions. And for large volume, for the large volume scenario, these calculations, actually, you can use it with the anti-D3 brane, and it reproduces some of the things we have had in the past. So it's less novel somehow, but still you can do the calculations and get the subsupersymmetry breaking. So, sorry for my voice, but I need more water. But, so, I will spend a couple of minutes on this slide because this summarizes the whole result. We have 4 scenarios: KKLT or large volume, the standard model is in D3 branes or in D7 branes. So the important thing is to see here is that some comments, usually the soft terms are usually people say are proportional to the gravitino mass. And here you can see that all of them are hierarchically smaller than the gravitino mass. So all the soft terms are smaller than gravitino mass. That's first thing. Second thing is that, take this case, these 3, the scalar masses and the Gaussian masses, they scale indifferently with the volume. So that means that the Gaussian masses are lighter than the scalar masses by a small power of the volume, a fraction of the power of the volume. So that means you have scalars heavier than Gaussians. Same thing here for large volume. The scalars, this is the square of the scalars, so the scalars of the Gaussians, that's the power of the volume to the 1/2. And the same thing here, the scalars and the Gaussians. So in that sense, 3 out of these 4 scenarios gives you what people call split supersymmetry that Nima has been promoting for many years. And and the 4th scenario gives you all the soft terms to the same order. So in that sense, that will be standard, similar to what the MSSM was. However, in this scenario, precisely the mass of the volume is so small that will cause cosmological problems, but it's called the cosmological modulus problems. So in order to have the mass of the volume to be high enough, this scale has to be higher, and this will give you a high-scale supersymmetry breaking. So supersymmetry breaking of the order 10 to 11 GeV or so. So none of them give you the standard MSSM of TeV scale sub-breaking terms. Either you have only TeV Gaussians and scalar much heavier, or everybody heavier. So that's essentially the summary of all this.
Is lambda tunable in that formula? What is lambda?
No. Lambda is just a coefficient of 1 power or something of one of the Kahler potentials. So it's fixed, yeah, or it's a further one. The only thing to worry here is this 1 minus 3 omega, because omega can be bigger than 1, but than 1/3, and this could be, at some point, it can give you tachyons. So all the other cases you're okay, but this one can give you tachyons. So essentially, so this is the summary. On top of that, you have to worry about the Brane-Antibrane interactions. And so you have a brane here and an antibrane there, so you have to worry if the presence of the antibrane can destabilize the presence of the 3 branes. We computed that, and it essentially just summarizing is essentially okay. You can just move a little bit the D3 brane just at length smaller than string scale, so it doesn't change, and you don't get tachyons if the scales if the soft terms are of the order that we get. So in that sense, everything is fine. And so for the phenomenology, for KKLT, as I said, there can be tachyons in the 3 branes, and then there are computation between alpha prime effects, which are the ones that we computed, and the anomaly mediation. So that's something that can be considered. For D7 branes, essentially, as I say, the soft terms are for the order of the subscalars are for the order of gravitino mass, and much bigger than the Gaussian mass. The modulus is heavier than the gravitino, and in that sense, the decay of the modulus or the heavier modulus can give rise to a gravitino cosmological problem. And the Gaussian masses, So the suppression of the gauge mass implies that the anomaly mediation is relevant. So that in some limit it can give something that people call mirage mediation, but it's only very particular limit, and it's not a natural. That's something that differs from what people have discussed in the past. And the natural thing you get is, what I said, is a split spectrum. The scalars and the gauginos the scalars are heavier than the gauginos by a factor of more than order 10 or so. For large volume, as I said, for these 7 branes, the modulus are lighter, so that means you can have a cosmological moduli problem, unless you have a large-scale supersymmetry. And for the D3 branes, you have, again, a split supersymmetry with the ratio of the scalars to gauginos of the 10 to the 2, 10 to the 3. So at the end, we come up with very few concrete scenarios. Split supersymmetry with only one or two orders of magnitude difference between the scalars and the gauginos, if you have the gauginos to be 1 TeV. This is interesting because when supersymmetry was introduced, the ratio between scalars and gaugino masses was supposed to be any value. Can be order 10 to the 5, 10 to the 10 or so, whereas here it's only very close. So that means that the scalars are heavier than the gauginos, but not too much heavier. And that's also good because it's consistent with the experimental results, because after the discovery of the Higgs, the parameter space of split supersymmetry is essentially kill most of it, except for ratios of this type. So in that sense, this is good phenomenologically. And of course, the motivation for split supersymmetry was assuming that there is something like the landscape and so on, and this is already built in the whole compactifications here. And the other scenario, which is less attractive, is that everything is of the order 10 to 11 GeV, which is not very. Sorry?
The Higgs mass come out too heavy.
No, I mean for these cases.
No. I mean that case is fine. In the high energy SUSY case, like 140 GeV.
No, I think this is about the right. This is about the right scale. Yes, that's a very interesting thing, because the Higgs mass puts very strong constraint on high scale supersymmetry breaking, and this is precisely in that regime where it can be. It rules out higher than this, but not this one. Yeah. And as I said, mirage mediation, even though it was motivated by this analysis, it comes out very, very, very rarely. So you have to tune some of the parameters to get it, otherwise you don't get it. Okay, so conclusions is essentially 2 main scenarios of supersymmetry breaking with computable soft terms. In the fully supersymmetric effective field theory with Nilpotent superfield. And so it's surprising that, first of all, KKLT existed for more than 12 years. These soft terms, in particular for D3 branes, had not been computed before at all. So in that sense, so you want to put something that you can eventually compare with experiments are the soft supersymmetry breaking terms, and you have to compute them in the scenarios that you can stabilize the moduli, and so this is completely new, and it's surprising that it has not, been achieved before, and. For the large volume, the results are similar to what we have had in the previous cases, except that now we can do it with anti-D3 brane in the same way that we had done it before. And in most of the cases, you get what people call mini-split supersymmetry. And I think, the rest, I don't have time to discuss the non-formal dark matter story that I could have mentioned. So, so thank you very much, and best wishes to Spenta for your future, and we hope to see you in ICTP more often now. Okay, well, thank you.
Early on in your talk, but what is the picture for supersymmetric gauge coupling unification in this whole scenario? When you have the standard model on 3 branes, there's no particularly good reason, is there, for the gauge couplings to unify?
Well, that's a good point. This is what I did here is just completely model independent. So in that sense, we didn't construct. Let's just say the standard model is either on D3 branes or on D7 branes. For gauge coupling unification, you have to go to concrete models and then see what happens. So in the type 2B, you have the 2 options. The standard model is on D7 branes or on D3 branes. If it is a F theory, then you can use, then you have a simple gauge group and so on. Here, these are just like intersecting branes or branes and singularities, then usually the gauge group is not simple. And so you have a product of gauge group. If the branes are at singularity, then you say that the gauge coupling is universal at the dilaton. So at least the leading order is unified. So branes and singularities have that property in that sense. There's
a limit where the dilaton dominates.
But the dilaton dominates, exactly. So in that sense, that gives you a unification. Yes, and there are concrete examples where actually you can achieve. So in that sense, you don't need to go to simple gauge groups to get unification.
Okay, thank you very much.